for example, we're going to work with, let's see, we're going to try to find the absolute extrema. That's the absolute maximum or minimum of f equal to e to the x squared minus y squared over x squared plus y squared less than or equal to 1. And so I know my first step is going to be to find critical points, which means I'm going to have to set my gradient equal to 0, where my gradient is going to be 2x e to the x squared minus y squared minus 2y e to the x squared minus y squared. And each component has to be equal to 0, so I know that this is going to give me a system of two equations that have to both be true at the same time. Oops, minus y squared. Okay. And these look about the same to me, so I'll just go in the order that they show up. 0 equal to 2x e to the x squared minus y squared. Something that I have to know is that exponentials are always bigger than 0. Here's like a drawing of e to the x. Here's a drawing of e to the minus x, but they're always going to stay away from the line y equals 0. So they can get very close in the positive or negative infinity directions, basically, but they're always greater than 0. So that right there is bigger than 0, which means the only way for this to be true is if 2x is 0 or x is equal to 0. And then in my second equation, again, this thing is always positive, so I need 0 equal to minus 2y, which means I need y equal to 0. And both those things have to be true simultaneously, so the point 0, 0 is the only critical point. I'm going to put a little box around that because it's important to me later. This is the point I found for step 2, find all critical points. So maybe I'll put like a little number sign there that says that's my first group of points I'll care about. And then I have to check the boundary points. So, hopefully you're pretty good at this point of picking out the thing that's f, and the thing that's left over is the statement of your boundary. But in general, it's going to include some sort of inequality, interval, something like that. And in this case, we're given x squared plus y squared less than or equal to 1 as our domain. So our domain is in the xy plane, this shaded in disk with radius 1. And my boundary is going to be the edge of the domain. So, oops. I had to think of all x squared plus y squared less than or equal to 1. That's shaded in circle. But when I'm looking for the boundary, it's just the edge of that circle. Okay, so it's just that outside. And that's x squared plus y squared equal to 1 is boundary. And the reason why we have to look at the boundary points is because the critical points are going to kind of tell us like important places where the function's behavior might change. But if we're restricting ourselves to a boundary, you could imagine that maybe you have like one of these funky bowl shapes, and the only critical point is at the bottom, it's a minimum. But if you cut off part of it, then clearly the highest values are going to occur wherever you stop drawing that bowl shape. And that's what this boundary point thing is for. So all collections of xy such that x squared plus y squared equals 1 form the boundary. That's coming from step 3, found the points on the boundary. And now my last part is to just check the value of f of xy equal to e to the x squared minus y squared at all points from my two different parts. And those points were 0, 0, or x squared plus y squared equals 1. So I'm going to start with 0, 0 because that's easiest. F of 0, 0 is e to the 0 minus 0 is e to the 0. That's cute. Is 1. So I don't have anything else to compare to yet, but I definitely know at the critical point 0, 0, the value of the function is 1. Next, I need to ask myself about what f of xy is for x squared plus y squared equals 1. If I'm on x squared plus y squared equals 1, then I know that y squared is equal to 1 minus x squared. So then f of xy is e to the x squared minus y squared is e to the x squared minus 1 minus x squared, or it's just e to the 2x squared minus 1 when I simplify this equation. And all that happened here was I took the y from my f of xy and replaced it with the y that shows I'm currently on the boundary. And if you wanted to, you could go ahead and just solve like a Calc 1 max-min problem for this function now. It's a function of only one variable, x. So you can find where it's biggest and smallest. But I'm going to do it a different way. I'm just going to think that, okay, my boundary was this circle. That meant x squared plus y squared equals 1. But now that I've written it only in terms of x, it means that x can be at smallest minus 1 and at biggest plus 1. So I already showed that I'm on x squared plus y squared equals 1. And if I live on that circle, then x has to fall between minus 1 and 1. And I just have to think about what happens to the function e to some power that depends on x as I move between minus 1 and 1. So if x equals minus 1, I'm going to get e to the 2 times 1 minus 1 is e to the 1, because minus 1 squared is just 1. And I'm going to get the exact same thing at x equals 1. F equals e to the 2 times 1 minus 1 is e to the 1. And that's the biggest e to the 2x squared minus 1 can possibly be, because x squared will always be a positive number. The biggest it can be is going to be when x is the biggest it can possibly be. And then you always subtract away 1 and multiply by 2, so nothing really changes. The smallest this function can possibly be is when x is equal to 0, because then I'm going to have e to the power of 2 times 0 minus 1 is e to the minus 1. And numbers to negative powers are small. And so at this point, I kind of have my answer. I know how to make f as small as possible, and I know how to make f as big as possible. And I'm just going to summarize that, and I have this like in-between value. Oops. So my absolute maximum is when f is biggest. And I know that's going to be f equal to e to the 1 is the biggest I can possibly make this function. And it's going to be when x is equal to minus 1 or 1, and y is equal to, we'll do that separately actually. So x is equal to plus or minus 1, and y is equal to 1 minus x squared. 1 minus 1 is just 0. So f of 1 comma 0 is the same as f of minus 1 comma 0 is e to the 1. That's where my absolute maximum is. And my absolute minimum is when f is smallest. And that's going to give me, let's see, f equal to e to the minus 1 was when x is 0. Y was equal to 1 minus x squared. Oops, sorry, y squared was equal to 1 minus x squared. So that's going to be 1. So that means y is equal to plus or minus 1 because y squared is equal to 1. So f of 0 comma 1 is the same of f of 0 comma minus 1 gives me e to the minus 1. And that's my absolute minimum. Minimum, maximum. This point that was our critical point was not the maximum or the minimum. It's not always going to happen that the boundary has the maximum or the minimum and the critical point ends up not being important. It'll flip between the two. So you do always need to check this point, even though for our specific example, it ended up not mattering.